Hello, everyone. Thanks for coming. We're going to talk about an introduction to deep learning. As the name suggests, it's just an introduction. So you may see some words that you may need to follow up, look it up, or reach out if you're interested. This is just an introductory to get familiar with the concepts. First, happy Halloween. And this is a little bit of information about me, especially my email address and my manager email address. If you need to follow up after our meeting, please reach out. We are under actionable analytics. A little bit of an overview. First, we talk about the general concept of machine learning, general concept of neural network. What is deep learning? When is it used? And some common deep learning architectures, or at least the concepts that you may, architectures that you may want to know before starting. Well, a little bit of motivation. Okay, so it all starts from the fact that we do not want to do any manual work. We struggle with manual work. And this is consistent across different industries, students, different people. If we don't want to have any manual work, the solution is automation. So people realize that they can have an automator tool like a mobile app or a software that they can save them a lot of time, and that would be the first thing in doing the machine learning. But apart from that, people know that the human brain have the ability to learn how to bike, how to swim. So if you want to have a machine, that machine should have the basically capabilities that the human being has. And there are three parts. Automation, our brain is able to automate once it learns something. We have intelligence, and then we can have a continual learning. Continual learning by itself, it's a big area. But to give you an area, like an idea of what that means is that whenever, let's say we are 3 years old, we learn how to speak. When we are 10 years old, we learn how to swim. But when we learn how to swim, we don't forget how we used to speak, right? So the skills that we learn just add up to each other. It doesn't overwrite itself. Where although that's a pretty straightforward concept in human brain, having that mechanism in a machine learning is a pretty hard task to do. But there are some mechanisms that when you learn something, it just adds up to the previous knowledge. I'm not going to talk about it in this talk, but for those who are interested, you can go into that. It has a pretty mathy mechanism. Okay, so if you look at the brain, there are three concepts in the brain, or three capabilities that our brain has. Detection, we memorize the stuff, and then we are able to generate. We have artists, we have poets that they generate poems. So if you want, if the idea of machine learning or artificial intelligence is to mimic the brain of a human, we need to address some of them by any solution that we propose, a subset of those. Hopefully all of those, but at least some of those. This is a pretty standard breakout difference between artificial intelligence as the more all-inclusive area to imitate human brain. When that is specific, when imitating the human brain is done specifically through a learning mechanism, that's a machine learning mechanism. And for the harder problems in machine learning that we cannot use the machine learning concepts, we go to more complex solutions, and that is the basis of deep learning. So a lot of people think that this is actually machine learning is a marriage between statistics and computer science. And so a lot of concepts that for those of us who want to enter into machine learning, you probably want to get well versed in statistics as well. And that comes pretty handy. So a machine learning process can come of these blocks. Probably all of you guys or some of you guys are familiar with these concepts, but I want to focus on two parts. That's the feature selection or feature extraction part when you get the raw data. you're probably the main job of the data scientist of your team to propose the features, which is done usually by someone in the field with the in-field knowledge. All the way you choose the model through an iterative process and you deploy the model, especially for those of us who also work on the engineering part and want to deploy the model and then have a recurrent inference. But that's kind of the process, the standard process, and a lot of pipelines that you would see out there. I would say almost all of them obeys the same architecture. And the machine learning algorithms are categorized in 4 different methods. These are the concepts above the machine learning algorithm. They are the way that you want to approach the problem, depending on whether your data has label or not, or reinforcement learning is an area which basically you want to learn from the environment the way we do in our daily life. When we are kid, we touch the fire and then we understand that's not good. So this kind of the same concept of here, but I'm sure a lot of you guys have seen that, so not a lot of details here. Everything stems from a very simple perceptron, and I would say that again comes from our human instinction. So let's say you want to make a decision in your life. You ask different people's opinions and different inputs, like those weights, depending on how you give importance to that person that you ask, you give weight to that person, you sum up all the information that you get from the people, and on top of that, you make a decision, right? And that's exactly that. You have inputs, you have weights, you sum up them, and on top of that, you make a decision. That thing that I say on top of that is the activation function, but I think we know what I'm talking about. Everything basically stems from that. Deep learning architectures, we will talk about that. They have many parameters, sometimes 140 million parameters, but if you delve into them, they're as simple as a multiplication or summation and all. Yeah. And then this is kind of the different activation functions that people use. Again, this is probably a little bit more detail for someone in the machine learning area, but each of those represents the way you make the decision. For example, the one which is called sigmoid, the most popular one, is the decision making of basically saturating the input data that you have. Again, at this moment, I think it might not be very intuitive for those of us who are new to the machine learning area, but you definitely want to look it up. There are actually a pretty good literature in that area, all from sigmoid, which is a very old activation function, all the way to mesh, which is more of a newer one. And neural network, which is nothing but an amalgamation of different perceptrons having input layer, hidden layer, and the output layer. So if you zoom in neural network, it's just perceptron. Okay, so the question is that then when we need to use deep learning, most of the questions that we get in industry are able to be solved by the machine learning algorithms. Only go to deep learning only if we need to. And if we can at least answer these questions. First, is the problem complex enough to go in that area, which I give you an example of a complex problem in the next slide. Second, do we have a big data? Because you will see or deep learning shows its benefit at big amount of data. At smaller amount of the data, you might end up just overkilling your resources. Third, how much resources you need? Resource of time, resource of your computation. You want to use GPU, CPU, what is your machine? And then what is the generality that you want? I think some of you guys are familiar with the very famous trade-off of bias and variance in machine learning, which basically says that the more complicated model you, the less complicated model you have, it's more general. The more you make it complicated, it's prone to some phenomenons or overfitting and everything. So that's the 4 questions that you want to answer yourself before deciding to go to the deep learning. Well, an example of a hard problem, which is often used in deep learning, is whenever you ask some people to write a digit 5, right? And then you want to classify that all of them are writing the letter 5. Obviously, different people write it differently. That's a very easy task for a human being, but that's a pretty hard task for the machine, mainly because you cannot teach a machine how a 5 is written. It's person to person. And I gave you this example because for those of us who are familiar with deep learning, we know that there is a very famous data set called MNIST, which is digits from 0 to 9. A lot of deep learning algorithms which are developed are being tested against that data set. So check out that data set and see how does it look. But how we are able to solve a hard problem, it's by a handshake between the big data and computing power. Because we have these 2 sources, we are able to solve harder problems. And this is the curve that I wanted to show you guys to tell you that why you need to do deep learning when there is a big data. This is 2 curves, you can find them online, that deep learning only shows its performance at the high amount of data, where the traditional algorithms, maybe even at the smaller amount of data, even you see the performance of the model might be a bit better, but it soon gets saturated. It does not mean that the deep learning algorithm does not get saturated. The more data you give, the more performance it will have, but it has been pretty standard practice to increase the data in order to the better data. Obviously, more amount of data means more amount of good data. So for a deep learning, basically task if you want to do, very important is actually making the ground truth data. It might sound, not a very important task, but you will see for those who are entering the deep learning, you will realize that sometimes it's very, very hard to find the ground truth data. For example, you want to do an ear detection mechanism, you might not find a lot of images on the data set. And that is why when you want to train big neural networks, you often use a pre-trained networks, which I will touch upon it when I'm talking about transfer learning. So you can leverage the pre-trained networks that have been trained on big amount of data. Hyperparameters tuning or parameters tuning is a quintessential part of deep learning. A quintessential part of deep learning to achieve the suitable performance. And finally, for a deep learning model, gauging the basically performance of the model in terms of running time, GPU usage, apart from RAK-UC and other metrics are very important. Because some of these deep learning models might take a long time to train, so you definitely want to observe that one. Okay, so what is good about deep learning is that for those of us who are doing machine learning, we know that we get an object, we definitely need a feature extractor, a physical person to propose the feature, then we build the machine learning model. Whereas in deep learning model, we need feature extraction, but we do not need the feature extractor. And that's a very big deal. The feature extraction is embedded into the model. You will see how it makes our life easier and gives us more power in solving the problem. You can just enter any field and build a model, and then you probably, if you're following the news on deep learning, you will see a lot of stuff in the medical field, which is very, very hard to achieve. It's being detected by the researchers in the deep learning area. So I said we don't need feature extractor, but we need feature extraction. So what is the feature extraction mechanism in convolutional in deep learning? It's based off a concept of convolution. Convolution has a mathematical definition, and is different than correlation. But convolution in the concept in the area of deep learning, at least the way it's being calculated, has a close relevance to the correlation operation. So we know that a lot of times, or most of the times when we are using deep learning, we use images as the input data. So we have different channels, RGB channels. We are familiar with that. The way we extract the feature is by doing a convolution operation on each of the layer of the image. So we have RGB channel here, input channel 1, channel 2, and channel 3. We use a kernel to extract these features. These kernels are carefully chosen, and at this stage, right now that I'm talking about, all of them have been developed. So you just need to use it. You don't need to think about it. But those kernels are in the way to capture, for example, the vertical edge of an image. So what is an image is some edges, vertical, horizontal edges, plus some intensity, right? Those kernels are being chosen in a way that captures some, for example, vertical edges, horizontal edges, a combination of those. And then all of them get summed up, for example, by a Bayes term, and then you construct an output. That output image is the extracted feature from this RGB image. Working with that output is like working with that RGB channel, which is way easier. And like I said, at this moment, all of these kernels are developed. All you need is just look for it, and you see that instead of needing someone in the field for feature extraction, you can just Google what is the corresponding. So we are going to talk about now that we are knowledgeable of convolution and neural network, we're talking about the convolution of neural network, a neural network in which the feature extraction is done being by the convolution operation, which I just mentioned. This is pretty much the standard typical vanilla convolution or neural network. It's a lot of information here, but I'm trying to talk about the main thing. Obviously, you have an input image, you have a kernel, which I just mentioned, the filter that goes through the different channels. This kernel then just swipe around the image from left to right, from bottom right to from up left to bottom right, and then depending on how this filter moves, there's a concept of a stride, how many pixels you move away. There's padding whenever you basically sweep over the image, the stuff on the borders might be. There are different mechanisms for taking care of that padding. That's another concept. You have pooling, and that's whenever basically the feature extraction happens. Whenever you do the kernel convolution operation on those images, the size of the data keeps getting increases. You can easily show that mathematically. By a pooling operation, you condense the image here, and you get a pooled feature map representation of your image, which is very important in diagnosing some problems like overfitting and all. The pooling layer is very important. Obviously, you can have feature maps, pooled feature maps stacked on top of each other. The number of layers, I put X3, 5. You can put as many as not as many as you want, which will be a problem with overfitting and all, but like 3 layers, 5 layers, they are stacked on top of each other. For those of us who are familiar with this area, there is a problem of vanishing gradient, which means that when you stack a bunch of convolutional neural networks, at some point the the network stops learning anything. Vanishing gradient means gradient vanishes, and gradient is a method, or stochastic gradient descent is a method for learning this concept. So people, I think, and for the first time in ResNet, people realize you can have a residual block to achieve that, to overcome that issue. And you have a flattening layer, then you have a fully connected layer, and then you put a softmax layer at the end to basically bring the values into some probability. Softmax layer, just think about how to basically represent the last layer of a neural network in terms of probability of association with different classes. As you move away from left to the right of this convolutional neural network, you are capturing more and more abstract features of the image. So if you look at the output of the feature map at the first layer, you should pretty much see the digit 5. But when you move away, and if you read the pooled feature image here, you might see something like that, because it's an abstract representation of image with compared to this one. Which is another important factor as well. The last couple of layers of a convolutional neural network, flattened layer, the fully connected layer, are those parts who are often fine-tuned whenever you have a new task. For those of us who are, I will talk about, but for those of us who are familiar with transfer learning, you'll see that any problem that you're trying to solve with deep learning, all you can do is that fine-tune the last few layers from a very well-known pre-trained network. Right. I think I talked about everything here. Yeah, that's the basic convolutional neural network. Obviously, people use it in different architecture for different purposes. So you want to look it up for further stuff. This is kind of the evolution of deep learning models. It all starts from perceptron that I talk about. It went from neurocognition, which was a hierarchical neural network. It went to the backprop as a very important concept in deep learning. Basically, it's a mechanism to learn, to update the parameters so that you can actually understand the underlying patterns. It was developed way before 1989, but 1986, but at that time it got, another rise and all. So very important, that's back propagation, propagating backward. So that's important concept if you wanna look it up. LeNet, a convolutional neural network. When it comes to 2010, probably some of you guys have heard of ImageNet, a very big database, which is used for training very well-known pre-trained networks. And since 2010, there is a competition of ImageNet that if you develop a new convolutional neural network, you can test it and see if you reach a higher performance. VGG, very important architecture in 2014, I think by a group in University of Oxford, I think. This is one of the important networks that a lot of tasks really right now for image classification and all is done by this model, a fine-tuned version of this model. ResNet, I think it's from Microsoft, if I'm not mistaken. For the first time, we're able to address the problem of vanishing gradient that I mentioned by adding a residual network. After that, 2019, there has been a structure of efficient net. If you remember on the previous slide, I just said a stack, a bunch of layers or how many filters, kernels you want to use that all. So one might ask you, should I increase the number of layers for a better learning, or if I keep increasing the number of kernels? Efficient net is trying to address that efficiently, how to efficiently choose those parameters. And then the recent area, which has been a combination of convolution and transformers. For those of us who are familiar with natural language processing, you guys probably have heard of transformers, a very well-known architecture, which was proposed, I think, by Google a couple of years ago, and that goes based off a mechanism called attention mechanism. That's for text, that's for natural language processing tasks, but people were able to bring it and then use it in conjunction with the convolution and convolutional neural network. So the recent architectures are based off that. Co-ATNet, that co means convolution and at means attention network. So if you want to use more recent architectures, just look them up and see if you use this mechanism. The transformers have been like a turning point for the field of natural language processing, the attention mechanism. So I highly recommend people go through that. And there's a company, Hugging Face, that provide those transformers pretty easy. Okay, so let's talk about the common architectures. Transfer learning is not an architecture, but because it uses the pre-trained model I put under here. Recurrent neural networks, autoencoders, and generative adversarial. If you remember, I mentioned the human brain has three aspects into that: detection, memory, and generation. Detection, you can use the convolutional neural network to detect the patterns, classify the images. Recurrent neural networks are for that capability of human being to memorize stuff. And generative adversarial network is for the capability of generating stuff. So, so far, we should be able to address those. Transfer learning is as simple as that. You transfer the learning into another area. You have a track detection, you have learned some features from that. You copy the learning parameters from the learned model and you bring it down for a new problem of detection, right? You just bring the parameters here, you have a fine-tuning area, and then you have a new problem statement. Now, let's say you have a problem in biology, you just need to basically find a corresponding good pre-trained neural network and tune that. And all of them are based off a concept that image is image, right? Flower and truck, they are two different things, but they have borders, they have edges and colors and everything. So definitely that would be your first basically approach for solving a deep neural network. Don't start from scratch. Just go ahead and see which networks are out there. A very important architecture, which is used a lot for transfer learning, is VGG by the Oxford University, Visual Geometry Group in there. And 16 means that there are 16 layers of the weights, right? If you count the gray letters and the green layers, there will be 16. The others are pulling. So very important. I think there is another version, which is G19 and all, but for those of us who are Python developer, that's very easy to pull it in Python and then fine tune it for your own purpose. So VGG and its combination. Another architecture which is used for transfer learning is the ResNet, which I talk about. ResNet also has some other versions, ResNet 50 and some other things. Again, that's very easy. If you are a Python developer, you just pull the model in Python. Okay, recurrent neural networks. Again, that's coming pretty much from the human brain. When I'm talking about something right now, I use the last bit of information to know what is my next word, and that's the basically concept here. The hidden layer or the output layer of the previous layer is used as one input to the next layer, and you stack these neural networks on top of each other. In its existence, it's a neural network. but it uses the previous hidden layers as the input to the next layer. Recurrent neural networks are notorious for having the problem of vanishing gradient, which I mentioned earlier what that is. So you probably don't want to use recurrent neural network by itself. You need, or you want to recurrent neural networks that problem is ameliorated. And one of those networks is LSTM. Probably many of you guys have heard of that. The problem of vanishing gradient was that the information from the very long past will be lost because of the vanishing gradient. So what they proposed is use the some gates, forget gate, input gate, output gate. So you get the information from the past. Now, let's say you have a very long sentence. The cat is hungry, it to eat something. This eat is referring what? To cat or something else. And because of the vanishing gradient, this will be lost. But this mechanism, the information from the past tokens or from the past input timestamps comes, and there is a forget gate that helps us to decide whether we should keep this information, it's important for this layer, or that's it. LSTM solves so there are two problems with the recurrent neural networks. First, that was the vanishing gradient that I mentioned. Second, that they are very time consuming to train. Recurrent neural network takes more time. And the problem of vanishing gradient is resolved by this structure, but LSTM is even slower to train than recurrent neural. So it solves one problem, but the other problem is still there. But LSTM networks are often used for time series prediction, and for those of us who are working with, not a very big data set, I think that's pretty much implementable even in your CPU machine. You shouldn't be worried about that. These are the applications of recurrent neural networks. Time series I mentioned, natural language processing. Before the transformers, they were used for speech recognition. Anything which has a component of memory and leverage the recurrent neural network. Language generation, text summarization, all of them can be done by recurrent neural network. I personally have always used LSTM for time series prediction, not for other tasks, but and it can give if you tune the parameters well. Network is auto encoder. So auto, there are two components into that. So this is more of generating an input of this. Think of that. You have a network that the input and the output are the same. So you are learning this pumpkin as in the training phase, both at the input and both at the output, right? And what is the purpose of that? For the purpose of this autoencoder is to find an encoded representation of that input image that you give, right? If I train the machine in a way that the input and the output are the same, and then I have a bottleneck layer which is going to summarize, giving a summary vector of that input layer. That vector is the basically principal component, the main component of the input image, right? Because I have been able to reconstruct it. At the testing phase, when you give that pumpkin, you might get a little bit of difference, right? A little bit of jitter, but that's because of the testing error. But the whole basically concept of autoencoder is to be able to find a extracted, a condensed version of the input layer. So it has an encoder and decoder part. For those of us who are familiar with the notion of principal component analysis, which you find a basically condensed, linearly condensed version of a data set. This does the same thing. And I think if you choose the activation function of autoencoders linearly, you will be to achieve PCA via autoencoder. The same concepts here. Right. Then once this model is trained, if you just keep the encoding part, you inject the input data, the output would be the encoded version of that and serve you as the network, but very easy to be implemented. What's an important concept? So there are 4 tools which we have using the autoencoders. First, feature extraction, like I mentioned, the bottleneck. The second one is denoising. So what is the purpose of the model? You give the input and output and the same image, right? The model has the responsibility to construct the output from the input. If that model is well trained, then if you put if you put a noisy version of the input layer, it should give you a denoise, right? Because the model is learned to is trained to find the corresponding patterns, right? If the model is trained to give you the output just like the input, and at the training time you have given them the non-noisy version. Now, if you give a noisy version to the model is trained to give you the actual one, which means it give you the denoised version of that. That's pretty handy. Anomaly detection. Again, this network is trained to give the output just like the input. If you have an anomaly in your data set, the reconstruction error of that particular example is anomaly anomalies with respect to the other data points which are not anomaly. So looking at the reconstruction error of the examples, you can get the anomaly data point. And image search. Let's say you have a big data set. Let's say Google has a very big data set, and you type dog, and it needs to show up, shows the dog. The way they can encode that dogs is by the encoded version of that dog, because it's encoded, it's a smaller version, and they can save that vector. And when you dog, they can translate it dog to a vector, let's say by some NLP method, and then find basically the most similar vector of what you wrote to the encoded version in their database. So they need a database, and that's a big thing. Google uses the same strategy. Autoencode, I highly set to look into that and implementing further. And this is two components. Generative, it generates, and there should be some combat, some adversarial part in short. Think of a person who is able to make or generate fake money, right? And then you have another resource like a bank that can generate the real money. This real money is then given to a police officer which knows what is a good money. With this information from that bank, the police officer now knows that this is a fake money. So there is always a competition and adversarial environment between the generator and discriminator. Now think of each of them as one neural network, as one neural network. They are trained both at the same time. The generator is trained to better and better make fake money. The discriminator is trained to better and better to detect the fake money. And they are simultaneously trained, which means that whenever a generator does a better job, the discriminator does a worse job, and vice versa. And all of them are translated to the loss function. If there are two neural networks, they have loss function. If you look at the loss function, whenever one of them peaks, the other one goes down. Whenever the other one goes down, Very hard, pretty hard network to train. So you definitely want to practice a little bit. And then definitely the real money that you have. Now, suppose this model is trained. These two networks are trained very well. If you just take the generator outside, that's a source for generating close to real money for you, right? If this model is well trained, means the loss function of the generator is so low that it's very hard for the discriminator to claim it as fake. So that means it's a real money, right? So that generator now generates for you close to real money. Now very helpful, you can use it as a poem generation. Let's say if you have trained a model and give it, you know, poems of Shakespeare or whatever, that part will be able to generate very close to Shakespeare for that. Very important concept, very important network, and basically it requires a little bit of work on that. I think that's it, and this is just to give you an idea of that with GAN, how much good you can do. I don't think you can easily say that they are not real images, right? Maybe from the background you get an idea and all. But what I'm saying is the GAN can make such fake images for us that's almost impossible for human beings to say it's a fake image. And there are some websites you can go, and I think there is also some game that shows you if it's real or not. I'm not sure if we can tell. But anyways, GANs are, if they are well trained, they can use easily for face generation, for style generation. A lot of I've seen people do that. They have two scenes. Let's say I'm here and there's another scene. They use GAN to, you know, bring them to the same thing, style learning and all. So that's one of the basically results of GAN. All right. So frameworks. I think probably all of us are, we want to do it in Python. I'm not sure if other frameworks have that. The most important, or the most recent and widely used architecture framework for deep learning is PyTorch. Before that, TensorFlow was there. Some people prefer to use Keras. Keras is a little bit on the older side, but very easy. You want to start with Keras, but for the most recent one, you can use PyTorch. TensorFlow is, at least to me, sometimes is not very intuitive. And so PyTorch, just go for PyTorch. There are Keanu, Cafe, and all. MaxNet, I personally have not used them, but I've seen people using them. But I think PyTorch should be good enough for you to be, you know, doing the state-of-the-art deep learning. All right. Okay, so I'll stop here. I know we have went through a lot of stuff, so if you have any questions.
So I have a question in terms of the feature extractor, right? So is the feature extractor specifically a function of deep learning? So are you always doing feature extraction with deep learning, or can you still use a human actor to identify your features as part of a deep learning model?
Okay, a good question. So if we don't do that, it might come back to the question of why we even need deep learning. If we want to have feature extraction, we might just do the machine learning. Note that deep learning is for the tasks that it's not readily intuitive for us. We let a machine do that. For example, like I mentioned, detecting number 5, it's a very hard task to be featureized. You want to say what at the top is that way, some person write it that way. And because we cannot rule those features, we need an automation tool, and those are the convolutional layers that we use. Yeah.
The answer is no.
If no question, thank you everyone for participating and have a great, have a great rest.